everyone. In this video, we're going to somewhat formalize the idea of limit. We're not going to go all the way. You can make really formal definitions and they're a little intimidating. But the idea behind a limit is not anything too crazy. So we're just going to go with sort of a loose definition. Okay, so the idea behind a limit and the notation is right here. So we have this whole limit as x approaches c of f of x is equal to L if f of x, which would be the y values of our function, get as close as we want to this y value L, so that's a y, when we make x closer and closer and closer to c. So c is an x value. So if we let our x's get really close to a specific x value, our y's should get as close as we want them to L. So for example, if I want my y's to be within 0.1 of L, I should be able to find a little chunk of x's really close to c for which that's true. All of those x values give you y's within 0.1 of L. So again, you read this, the limit of f of x as x approaches c is L. Or you can say the limit as x approaches c of f of x is L. Either of those is fine with me. So again, this is the y value that our function approaches when our x gets really close to c. Really important, if our function doesn't approach a single value, when we look at the two sides of x equals c, things a little bigger and things a little smaller than c, then the limit does not exist. So this d and e we'll have to use whenever we get different y values on either side of x equals c. So discontinuities are going to be potentially trouble for us. One other really important thing to notice here is that saying the limit of f of x as x approaches c is L does not tell us that f of c is L. So it doesn't tell us anything about the y value at x equals c. Again, we want to picture something like this. So if this is x value c, y value L, just because the y values are getting really close to L doesn't mean that f of c will be L. So you got to remember that this is not just plugging in an x value. This is looking nearby an x value. That's the whole interesting thing. Okay, so to practice this a little bit, I want to do a graph function. So we're going to review piecewise functions a little bit here, and we're going to sketch the graph of this thing, and then we'll evaluate some limits. So I made us a nice messy one. I made us a piecewise function with 4 different pieces. Okay, so let's see. We want this to look like cosine of x when x is less than 0. So cosine of x goes through 0, 1. We're going to cut that off with an open circle. And then it would go through, let me think about this. So it would go through negative 2 pi, 1 as well. So negative 3 is here. So right around here is about negative 2 pi, 1. It would go through, oh, no, what am I saying? That's negative pi. Okay, let me try that again. It would go through negative 2 pi, which would be about here, negative 2 pi, 1. Negative 2 pi is about negative 6.28. Okay, and then it would go through pi, negative 1. Negative pi, negative 1 even. And in between, at about 1.57 pi over 2, it would cross, and then halfway in between these, so we'd have to go about 1.57, it would cross. So there's a decent rough sketch of that part of the graph. So it looks like a cosine wave, but only if your x values are less than 0. After that, we actually only get a single point here. We get the y value of 2 when the x value is 0, so that's one single point. Y value is 2 when x value is 0. We then, from x equals 0 to x equals 3, so this little chunk right here, get a straight line, y equals 3 minus x. So this is a line with a slope of negative 1 and a y-intercept of 3. So it's going to start here with an open circle, because this is strictly greater than. And then we're going to head off with a slope of negative 1 until we get to x equals 3. So there's piece number 3. And then the last one is a little bit tricky. It's a reciprocal function, a 1 over x function, which would look something like this. It's been shifted to the right 3. That x minus 3 means shift to the right 3. So this vertical asymptote that was at x equals 0 actually moves over to x equals 3. And then we only want the stuff to the right of that. So this piece right here, and if you want a specific point, this 1 over x function, that's what I'm looking at, the basic function, goes through 1, 1. So if I shift it right 3, it would hit 4, 1. It would have the horizontal asymptote still on the axis. Okay, so there's a graph of my function. The limit part of this comes into play when we try to answer these questions. So we are supposed to look for, first, the limit as x approaches negative pi of f of x. So negative pi right around here. We've already identified the point on the graph. So the question is, as our x's get really close to negative pi, what are our y's getting really close to? And this one's not very exciting because the function's nice and continuous at that point, so it really will just equal the y value, negative 1. But whenever your function is discontinuous, this limit business becomes a really interesting question. Okay, so second one, what about the limit as x approaches 0? So now I want to look at what happens as x gets really close to 0 from the left and really close to 0 from the right, and hopefully you're spotting that this one is a little more interesting. There's a discontinuity here, and on the left I'm approaching a smaller value than on the right. So this is automatically, it does not exist. If choosing numbers a little bigger and a little smaller than the specific x value you're interested in gives you a big difference in y values, big being even like 1 apart is big. We want to be able to get them infinitely close. That's going to be, it does not exist. Okay, but we don't just have to throw away the information that we looked at here. We can talk about the limit from only one side, and that's what this notation means. So this little superscript plus sign means from the right. So you think about coming from the plus side, the big positive numbers, and you work your way in here and you let your x get really, really close to 0, staying on the right-hand side. And I do have an answer as long as I only have to look at the right-hand side. My answer is 3. As x approaches 3 from the right, my y values get really close to 3. I'm also asked right here, this is from the left, to look at the other side. So if it doesn't have the little superscript, the little like exponent plus minus, you're supposed to look at both sides. But if it does have that, then you're allowed to look at only one side. So over here, as x approaches 0 from the left-hand side, it looks like my y's are going to get closer and closer to 1. Okay, all right, let's do different colors for our different lines. Last one, we're supposed to look at x approaches 3. So x approaches 3 is right here. And the first question is just what happens as x approaches 3 in general. So if we look at the two sides, as x gets closer and closer to 3 from the left, we're getting a very different result than what happens as x approaches 3 from the right. So this is another does not exist. Unless you could say they're both approaching the same thing, you're out of luck. So let's go ahead again and look at the left-hand side and then the right-hand side. So this one, as x approaches 3 from the left, so we start on the left-hand side and we work our way towards x equals 3, our y's are going to get as close as we would like to 0. They never actually equal 0. There's an open circle, but they can get as close as we want them to. And then as x approaches 3 from the right, the closer our x gets to 3 on the right-hand side, the bigger our y gets. So we would say that the limit is infinity. And this is kind of a funny one. I've worked with calc books before that would say it does not exist if it's infinite. I think part of the problem here is saying something equals infinity seems a little questionable since you're never supposed to be able to get here. But I've also worked with calculus books that just say what we mean when we say the limit equals infinity is that if you get x close enough to 3 on the right-hand side, you can make your y as big as you want it to. There is no end to how big you can make your y by getting x really, really close to 3. So vertical asymptotes, you can get infinity as an answer. Just be aware, if you look back up at this graph right here, that if we took the limit as x approaches 0 here, it would be a does not exist unless we made it one-sided, because one side heads to positive infinity and one side heads to negative infinity. So we could come from the right and say infinity, or from the left and say negative infinity, but if we're supposed to look at both, that would be a does not exist. All right, thanks for watching.